In a previous video, we learned that a changing magnetic flux through a loop of wire will create a voltage in that loop of wire. Now, there are several ways we could change the magnetic flux through a loop of wire. If our magnetic flux is due to, for example, a magnet or some other source of magnetic field near the wire, if we move the magnet around, well, that will change the strength of the magnetic field around the wire, and that will cause the magnetic flux to change through that wire. Another way we could change the magnetic flux through a wire is to change the surface area of the wire. So you can imagine maybe this wire were conducting but made of some elastic material that could stretch or shrink. In that case, that would also be another way we could change the magnetic flux through our wire and create a voltage through that wire. A third way we could change the magnetic flux through a wire is to rotate the wire. If we change the orientation of the wire, that would essentially be changing theta in the equation for magnetic flux, and that would change the number of magnetic field lines that pass through the wire. Now, the amount of voltage we create is technically the EMF. For the purpose of this course, as I've been saying, we could interchange the idea of voltage with the idea of EMF. I don't consider them to really be any different than each other because we assume ideal scenarios for our calculations. Whenever any quantity changes in physics, that quantity will not change instantaneously. That quantity will take some interval of time to change. So if I go from an initial flux to a final flux, I have some amount of change in magnetic flux, and that change will take place over some interval of time. So I also have a delta t. So the amount of voltage I create, the EMF, this curly E, is directly equal to the rate of change of the magnetic flux through this wire. Now, what we say is we induce a voltage in the wire. So inducing a voltage, you could, as a mental picture, pretend somebody's plugging in lots of little batteries in this wire. Now, we know from previous chapters that if you put batteries in a wire, that will cause a current to flow around the wire from Ohm's law. So inducing a voltage implies the existence of creating a current through this wire. Now we have an induced current. And we learned in the previous chapter on magnetism that moving charges create magnetic fields. So if I have current flowing through this wire, this wire will create its own magnetic field. So now I have two magnetic fields. I have the original magnetic field that was responsible for the changing magnetic flux. That is the magnetic field created by this bar magnet that I'm moving around in the picture. And I have an induced magnetic field. This induced magnetic field will be created by this induced current that's flowing around the wire. In my opinion, this PowerPoint slide was the important PowerPoint slide from the first part of this chapter. The other thing we did when we were going over the slides in a previous lecture was we just wanted to think of a way we could be efficient. What if we want to create a lot of voltage? And one way we could create a lot of voltage is to use a really huge wire with a really large surface area. Now, to have a really large wire would not necessarily be practical because it would be tough to have a magnetic field changing over that really large wire, but we could effectively mirror a large surface area by just having lots of wires that are all stacked on top of each other. So we took Faraday's law, which tells us how much voltage we create in the wire, and we just generalized that equation to allow us to possibly have more than one wire. So the amount of voltage we create is equal to the rate of change of magnetic flux times the number of loops of wire we have. We also had this negative sign, and the goal of this part of the lecture is now going to be what direction does the current flow through this wire? Will the current flow clockwise or counterclockwise? And this is the source of the negative sign here. So we learned that a changing magnetic flux will induce a voltage in the wire, it'll induce a current through the wire, If you're going to get charges to move, you got to push on them. If you want to impart a force onto a charged particle, well, you do that by setting up an electric field. So we could say there is an induced electric field as well. And an induced electric field and induced current imply the existence of an induced magnetic field. So what direction will the current flow when the flux changes? And all of these quantities listed above are related to each other. Ohm's law implies that if we have an induced voltage, we will have an induced current. And the induced voltage, if that changes by some amount, the induced current will change by some amount. The wire itself is made of some real material made out of atoms, so the wire will have some amount of resistance in it. That resistance will often be very small. It might only be 1 ohm or 0.1 ohm, but that resistance will technically be something other than 0. So if we have some amount of voltage, we are going to have some amount of current, and when one quantity changes, the other quantity will change in lockstep. And we could make the same statement as above with regard to the other quantities as well. If the current changes, then the magnetic field will change. So, how do the directions of these quantities relate to each other? Well, there is a very direct relationship between the direction of voltage and the direction of current. In a previous chapter, we used Ohm's law, and we said if I have a circuit and I have some batteries in that circuit oriented clockwise, then the current will flow clockwise. So I could think of that as saying whatever direction the voltage is in, the current will flow in that direction. Now, it's not entirely proper to talk about the direction of voltage, but you could imagine in this picture here, I have the batteries drawn in a counterclockwise direction. And so if I plug all my batteries, if I have my induced voltage pushing the current in a counterclockwise direction, I know the current will flow in a counterclockwise direction. Now, if I know the direction of the induced current, I could use the right-hand rule, align my thumb with the current, curl my fingers around the wire, use the right-hand rule to find the direction of the induced magnetic field. Now, all of these quantities are related to each other. So in other words, I could say if I know one of these directions, I know all of these directions. Because if I know the direction of induced voltage, I know the current will flow in the same direction. And once I know the direction of the current, I use the right-hand rule to find the direction of how the magnetic field wraps around the wire. Or conversely, if I know how the magnetic field wraps around the wire, there's my 4 fingers, my thumb will point in the direction of the current. And if I know the direction of the current, I know the direction of the voltage. So we just have to ask the question, how do we find one of these? Because once I know one of these directions, I have a rule, the right-hand rule, or V equals IR to find the direction of the other two. Now, before I tell you how to find the direction of these quantities, I'm going to show you one trick. Now, in the last chapter, you saw a picture of a solenoid that looks like this. And we said that if you align your thumb with the direction of the wire, your 4 fingers will be the magnetic field wrapping around the wire. This statement still holds true, but when we have a loop of wire, we could reverse the roles. So if we wanted, we could have our 4 fingers wrap around the solenoid or wrap around the loop of wire, and we could have our thumb point through the center of the loop. And if you think of the solenoid, I have current coming out of the top of the solenoid, and then current is flowing into the screen on the bottom of the solenoid. And if I orient the 4 fingers of my right hand so they're coming out of the computer screen up here and curling into the computer screen here, I notice my thumb will point in the same direction as the magnetic field through the center of the solenoid. So in earlier lectures, I was talking about you have a straight part and a curly part. You align your 4 fingers with the curly part and you align your thumb with the straight part. If I have loops of wire, I could have my 4 fingers be the loop and my thumb will be the magnetic field through the center of the wire. If I have a long straight wire, I could have my thumb be the current flowing through that long straight wire and my forefingers curl around the wire as the magnetic field. Now, both of these methods will work. You have a straight part and a curly part. The straight part is your thumb, the curly part is your forefingers. Now, if the wire's in a loop, I could have my forefingers be the loop, and then the direction of the magnetic field through the center of the loop will be my thumb. So if I have a straight part and a curly part, one of those will be the current, the other will be the magnetic field. And once I know which one is, the other is automatically set for me. So if I have one or more loops of wire, I could curl my forefingers in the same direction as the current through that loop, or I could point my thumb in the direction of the magnetic field through the center of the loop. And it doesn't matter which quantity I know. If I know I, then I could find B, or if I know B, I could find I. So knowledge of the direction of one of these quantities of current or magnetic field will automatically set the direction of the other quantity. So how do we determine the direction of one of these quantities? The rule we use for determining the direction for these quantities is through Lenz's law. And Lenz's law says basically that nature will oppose a change in magnetic flux through my loop. Now, Lenz's law is often stated in a longer form, in more words, but this is basically what Lenz's law boils down to. Originally, I will have some amount of magnetic flux through my loop, and that magnetic flux through my loop is going to change because I'm moving this magnet around. The magnetic flux through my loop is going to change. Nature will oppose that. So the direction of the induced magnetic field will attempt to keep the flux through my loop unchanged. So what might that look like as an example? Let's say we have a loop of wire and we have a magnetic field passing through that loop of wire. So let's say this loop of wire has a total area of 1, just to make numbers simple. The strength of the magnetic field is 0.25. So, okay, I have a 0.25 magnetic field through a loop of cross-sectional area 1. Now let's increase the strength of the magnetic field to 0.5. So the magnetic flux through this loop has increased. So the original magnetic field got stronger. The magnetic flux through the loop of wire increased. Well, what direction will the induced current flow, clockwise or counterclockwise? Okay, we increased the strength of the magnetic field through this loop of wire, so nature will oppose a change in magnetic flux. So to try to keep the magnetic flux through the wire as what it was, nature will have the induced magnetic field be pointing into the page. So if the magnetic field points into the page, well, the curly part is going to be the loop of wire. The straight part will be my thumb into the page. So if I point my thumb into the page, the right-hand rule, my fingers are curling clockwise around the wire. So the induced current in this wire will flow in a clockwise direction. What about this scenario? I have an initial magnetic field passing out from the computer screen towards you. I have a wire with a cross-sectional area of 8 meters. I shrink the size of the wire. Now I have a cross-sectional area of 2 meters. Well, the area of my loop has decreased. So therefore, the magnetic flux through my loop has decreased. Well, nature is going to oppose this. So the induced magnetic field the flux got small. The induced magnetic field will try to keep the magnetic flux through my wire big. So Lenz's law says that the induced magnetic field will attempt to increase the flux through my loop to keep it what it was previously. So the induced magnetic field is going to point outwards towards you. Now, if I point my thumb in the direction of the induced magnetic field, my four fingers will curl around the wire in a counterclockwise direction. So that implies from the right-hand rule, my thumb is the straight part through the center of the wire. That's going to be my magnetic field. My four fingers curl around the wire, so my four fingers are the current. And so the induced current is flowing counterclockwise around the wire, and therefore the induced voltage is going to be in a counterclockwise direction.